Hi, welcome to Why Physicists Are Good at Managing Uncertainties, Part 1. Let's start here. I'm claiming in this video that physicists are good at managing uncertainty. What does that even mean? Here's an oversimplified way of putting it. Physicists are good at having an idea of how good their knowledge is. There are a couple of things that physicists do regularly that require being good at managing uncertainty. The first of these is drawing conclusions from necessarily imperfect experimental data. The second is making simplified models of phenomena and knowing how good those models are. We're going to cover the first of these in this video. The second will be covered in the next video. Okay. In science, a rough picture of what we do is the following. We see some phenomenon in nature and wish to explain it. We make a hypothesis to explain the phenomenon. We then test the hypothesis via experiment and/or observation. If the hypothesis agrees with the experiment or observation, we keep it around for further tests. If it disagrees, we discard it. But it's not that simple. There are uncertainties on both the observation and the prediction of the hypothesis that you're trying to test. That means that answering this question of whether the hypothesis agrees or disagrees with the experiment or observation is not necessarily straightforward. Answering that question means we have to compare imperfect predictions against imperfect measurements and still draw conclusions. The key to doing this is knowing how imperfect the predictions are and how imperfect the measurements are, and then reporting both the conclusions and how certain you are of them. So we need to quantify the uncertainty in the predictions and in the measurements, and then quantify the uncertainty in our results. Instead of just saying if a hypothesis agrees or disagrees with observation, we report how well it agrees or how badly it disagrees with observation. So, roughly speaking, physicists need to be good at knowing how good their predictions are and how good their measurements are, and at quantifying how strong their resulting conclusions are. Okay, let's give a couple examples. Okay, example 1. Let's say a particle physicist comes up with a new hypothesis to explain some phenomenon. If this hypothesis is true, it will affect the rate of a certain process in particle collisions at the Large Hadron Collider in a way that can be calculated. So we measure that rate and compare it with the predictions of the hypothesis. But it's not that we check to see if the measured and predicted rates give the same number. The measurement will have an error bar. Let's say we've plotted the measured result with its error bar on the right. The prediction will also have an error bar. Do these predicted and measured values agree or disagree? Or more accurately, how well do the predicted and measured values agree, or how badly do they disagree? Answering this question involves understanding the precise meaning of the quoted uncertainties. We'll see precisely what they mean in a later video. Once we know that, we can quantify how compatible this prediction and measurement are. Physicists have to do this all the time to decide to keep or reject scientific hypotheses. Okay, example 2. Let's say we have a scientific theory of some natural phenomenon that has passed a wide variety of experimental tests. And then someone comes up with a new idea, different from the existing theory. Perhaps it addresses some unsolved mystery. It predicts values for some measurable quantities that are slightly different from those of the existing theory. Measurements of these quantities already exist, and they are in agreement with the old theory. Do the pre-existing measurements say anything about whether this new idea is worth pursuing? Let's look at one of those pre-existing measurements. Here we have the prediction of the old theory for some quantity that we can measure, and we also plot the prediction of the new idea. Now we said that the pre-existing measurements agree with the old theory. Now the uncertainty on the previous measurement may be large enough that it is compatible with the new idea. Or it might disfavor or rule out the new idea from the start. Here we see a case where the pre-existing measurements strongly disfavor the prediction of the new idea. This means that when proposing a new idea, physicists need to understand if uncertainties on pre-existing measurements indicate the idea is already ruled out. Or, put another way, physicists need to know how well the old theory has been measured so they know how different the predictions of the new ideas are allowed to be from the old ones. This is also important for future measurements. For example, a hypothetical future measurement may have an error bar that is small enough to disfavor or rule out one prediction or the other. On the other hand, it's possible that the future measurement will have an error bar too large to discriminate between the hypotheses. In such a case, the experiment may not be worth its perhaps considerable cost. So physicists need to be able to determine what they can conclude from experiments before they even build them. So physicists have to be able to compare a prediction and a measurement where that prediction and that measurement both have error bars and still reach a conclusion. And for that reason, when reporting a scientific result, it is not enough to simply give our conclusions. We need to also quantify how certain we are of those conclusions. Accomplishing this requires being able to interpret information and the uncertainty attached to that information.